people? Well, I'm going to assume this knowledge next week, so hopefully everyone has a chance to look at it before then. So I'm going to pick up where I left off with statistics review. And does anybody have any questions? So we left with looking at this, identifying the 5 features of the distribution, and we talked about the shape, and the shape informs the center, and it also informs the spread of the distribution. And we're going to talk about spread, measures of variation, because the median is not enough. It's just one value. If you calculate the median here, it's just one value. What about how the values are spread out? Because there's a whole distribution of numbers here in a range from 2 to 69, right? So that's why we use the spread, and I'm going to demonstrate how to use it, but I want to work with the symmetric data because that's really what we're going to work in finance with. The other feature is the gaps and outliers. Now I'm not going to talk about these, but these are the important elements of a presentation or a summary of data. Gaps and outliers and any peaks. And with that information about extreme values and any gaps that separate the extreme values from the rest, that gives you an idea that these are strange, and there's even a way to check if values are statistical outliers, and we'll talk about that. And then mentioning any peaks is really important because it tells you about behavior of groups of data, and there's characteristics there that differ among the groups that you want to explore. So let me just summarize. In data that's skewed for the spread, you want to present what's called the 5-number summary, which consists of the percentiles, the quartiles of the distribution. For gaps and outliers, you want to comment, and here there's one gap between 55 and 59. And outliers, we would need to verify extreme values to see if they are, in statistical terms, statistical outliers. And peaks, we're going to identify 3 peaks and say that they represent possibly low, middle, and high income earners, but we'd have to investigate. Because just what people spend doesn't necessarily mean how much they make. Maybe these are not even households at all. Maybe these are other businesses that are buying some items for their production as inputs to production. So maybe these are restaurants buying some of the groceries or some of the condiments to make meals in the restaurant. Who knows? All right, so what I'm going to do next is talk about a symmetric distribution, okay? So because we end up focusing on symmetric distributions, and when data are symmetric, we use the mean. And as a measure of spread, we use the standard deviation. So when we want to describe how a list of numbers is spread out around the center, we use the standard deviation when data are symmetric. When they are skewed, as in the above example, we would use the median, and to describe the spread, we report the median, the minimum, maximum, and the 4 quartiles of the distribution. And we talk about the middle data being from third to first quartile is 50% of the data. And that would show you the regularity in the data, and then you can talk about the extreme values as curious, and you can investigate those. Now, in a symmetric distribution, we report the mean as the center and the standard deviation as the spread. The standard deviation is the square root of the variance. What is the variance? The variance is the average of the squared deviations from the mean. So, I'm going to demonstrate what this all means and why we do it with this example. Here is the formula for mean and standard deviation. This is the symbol sigma. It's the capital letter S in Greek. And here it implies sum. So you want to sum all the observations. X represents each observation with a subscript I, telling you to go through the observations and sum them, and then divide by n. So whenever you see this symbol, a summation and an n on the bottom, this is an average. In this case, it's a sample average, but it's an average nonetheless. Statistics is about averages and relative measures. That's what it's about. So you need to be able to read statistics. And when you see something like this, sigma with an n on the bottom, or some n with maybe, close to n value, you know you're averaging. So this is the sample average or sample mean. And here is the sample standard deviation. So what is the sample standard deviation? We see here the same thing as here. You see a summation and an n on the bottom. You also see that here. It's n minus 1, but we'll talk about why that is. But still, it's like a summation and dividing by n. We'll talk about why it's one less. And what is it averaging? It's averaging this. It's averaging this amount that's known as the deviation from the mean. So what we're doing is we want an idea of spread, and what we want to know is how spread out are the data relative to the center, the mean, when data are symmetric. So we're going to measure the deviations from that center, and then rather than just average them, we have to do a couple of other things. One is square them, and the other one is divide by n minus 1. So I'm going to explain what's going on here. So here's an example. So this is how much money a student has in their pocket during a week, and we'll use it as our sample. We want to estimate how much potential or how much change an individual might have to spend in the cafeteria for snacks. So Monday, the person has $2, Tuesday $8, Wednesday $10, Thursday $16, and Friday $5. So we have to make a comment first that, there's only 5 observations here, but we have to make sure that whenever we calculate the mean, it has we have to justify that we have a symmetric distribution, right? Otherwise, it's not the right measure. And this all makes sense when I'm done, by the time I'm done. But, okay, so we have 2, we have 5, we have 8, 10, and 16. And the question is this evenly spread out? So between here and here, there's about 8 values, right? There's 8 values, and between here and here is 6. So it's not perfect, but let's see if it's balanced. So between here and here is 3, and here is 2. So, okay, roughly it's spread out roughly symmetrically. So like it's a little bit more here on the outside, but in the inside, it's a little bit more to balance off on this side. So they sort of balance each other out. So we call this, we'll just assume symmetry in the data. So now we can take an average comfortably. So to get the average, we use our calculator in stat mode. Now, depending what calculator you have, I'm going to use my TI BA2 Plus. And in this calculator, there's a key. I already have information in there. If you hit second data, it activates stat mode. Depending on the calculator you have, activate stat mode. In this case, I have to clear the worksheet. And I begin to enter the values. So it's 2, 8, 10, 16, 5. So 2. Okay, so it's asking me for the other variable because this is a 2-variable calculator. And I don't have a variable right now. We're going to do that later. But right now we just have one variable, so I don't put anything there. I leave it as 1 and continue to scroll down. So that was the first value. 2, 8, 10, 16, 5. 8, 10, 16, and 5. So you have that, and now you ask for the statistical results, so stats, and it says LIN. LIN stands for linear, so it assumes that you're asking for the correlation estimates, correlation between X and Y, but I only put one variable in there, so I'm only going to extract the information for X. First, it tells me there's 5 observations. Then it tells me the mean of X, 8.2, and it tells me this, standard deviation, 5.31. But it also tells me this, 4.75. So which one do I use? Is it this standard deviation or is it this standard deviation? No comments? So this has S and this has sigma. Whenever you see the Greek letters imply that it is a population parameter. So this is the value I want, but what is this one? So the value I get from my calculator, the values I get are X bar equal 8.2, which are $8.20, and S, which is equals $5.31. It also told me sigma which was equal to 7, oh, that didn't work, 475. And I told you this is the one we want because this is just a sample. If it was a population, all of the data, we would use that one. But we don't have all the data, we just have a sample. So we use this one. It's important to notice that ours will always be bigger. The formula used for sigma, the population standard deviation, is actually like this. If I had all the data, so for instance, if I had all the GPAs of students at the UPR in finance, then I would use this calculation to estimate the standard deviation. And I would use this calculation to estimate the mean. So I put a large X because those are actually the values. The little x means just observations. These are all the values. This is the true mean, and then this is the actual population size. So if I had all that information, I should use this formula and this formula. But I don't. I just have the sample, and most of the time you will only have the sample. So because of that, you have to substitute the true mean for the sample mean. Or say it the other way. I have to substitute the sample mean for the true mean. I have to use the sample mean instead of the true mean. And when I do that, for every estimate inside of an estimate, I lose a degree of freedom. Each observation introduces a degree of randomness or degree of freedom. And when I tie them together by calculating something like the sample mean that ties them all together, I lose 1 degree of randomness. And if I have to reduce my sample size by 1. And what this effectively does is allows the standard deviation to be a little bit bigger. And it'll make sense once I show you how we use that. It'll make sense why we do that. We want to be able to account for the spread, how spread out the data are, and this allows us to catch more than using the population standard deviation. So we don't use this, we use these two. But I already have my answer, so why am I going to do this? I want to do this exercise in calculating with the table to demonstrate the nature of this formula. So hopefully you don't forget, because again, statistics is about averages and relative measures. It's very important that you understand this foundation so you can easily breeze through statistics because you see these patterns. And you appreciate what it is that's going on when you get a more complicated looking statistics or formulas for statistics. So what we do is say, okay, well, we have the mean, we have the center, and now we want to know about how spread out the data are and have one single figure, one single number representing that spread. So what we're going to begin with is calculating these deviations from the mean. Now, that's not the mean. The mean is actually $8.20, right? The mean is actually $8.20. So I'm going to calculate the deviations from the mean for each one of these. And what you get is that, now you could do this in Excel, but I don't expect you to do this table calculation every time. This is just to make a point. I want to make a point to you. And that is, the point is why we do this. Why we do this way. So if I have the deviations from the mean, why don't I just calculate the average of those? What is the total sum of all of these values? So if you add these together, and you can do that in your calculator if you want. Going to second data and then second clear work and entering those values. 620 negative, enter down, down. 0.2 negative, enter down, down. 180, enter down, down. 780, enter down, down. 3.2 negative, enter down, down. And then ask for the results. What do you get? So I'm going to clear, second clear, so it's clear now. And I'm going to enter the data. So 6.2 negative, enter down, down. 0.2 negative, enter down, down. 1.8, enter down, down. 7.8, enter down, down. 3.2 negative, enter down, down. And then ask for do you have a question on Hal? Just write the question. So going through my results, the mean is here. The mean is 0. Did I make an error? Going through my data again, making sure I didn't make an error. I didn't make an error. The mean is 0. Now, was that a coincidence that the mean, not the mean, but sorry, the mean. I guess that's the mean I wanted. So it turns out that the mean is 0 because the sum is 0. Now, is that a coincidence or is there a reason for that? So after you put all the x's, you hit second stat. And then you scroll and see the results. And it turns out that I will get a total of 0 and obviously a mean of 0 as well. So it turns out that if I just take the deviations from the mean to try and find the average deviation from the mean, I'm always going to get 0. So this is not going to work. Why is this not going to work? This is not going to work because of the nature of the mean. Remember that the mean is the center value, the center of gravity, the point closest to all the other points. So on both sides, the deviations on the left and the deviations on the right will perfectly cancel each other. Always. So these will always sum to 0. The mean will always be 0. So to avoid that, we have to basically deal with the fact that some are negative and some are positive. We could just make them all positive, and some statisticians came up with results doing that. But the convention became to instead, to get rid of the negative, they squared the deviations from the mean. So what we'll do is get the squares of the deviations from the mean and average those, but then, we have to adjust something here because we can't leave everything squared. When we squared values, we also square their units. Notice, up until this point, all we have are dollars. These are dollars all the way down. These are dollars all the way down. And so deviations from the mean are dollars. What happens when I square them? So if I start squaring to get rid of the negative sign, what are the units? Remember to refresh your screen if it gets blurry. So no idea what the units are? Well, the sign The symbol here, the units, are actually going to be units squared, so it would be dollar square, but that doesn't make any sense, so we just don't write it. What we do instead is we remember that we need to take the square root when we're done. Okay, we have to take the square root when we're finished to remove that symbol squared, or those units squared. So we proceed with what our goal is, to get an average of the deviations from the mean, because we assume the distribution was symmetric. So these deviations from the mean should be symmetric, and the squared ones, now we're going to average those, because we assume that we can do that. It's still symmetric. And when we average them now, we have to use the fact that we lose 1 degree of freedom as a consequence of substituting x bar for mu that we don't have, because we don't have all the data. So we average, I put quotations around average now because we have made an adjustment in degrees of freedom. So the total, find the total, the sum. Again, you can use your calculator if you want for practice. Clear work. I think this is a mistake here. (1.8 squared) is 3.24. Sorry about that. Okay, so then to add them together, so go back to entering data, clear work, and enter $38.44, enter down, down. 0.04, enter down, down. 3.24, enter down, down. 60.84, enter down, down. And 10.24, enter down, down. And then ask for statistics, and you get, oh, did I do something wrong? Something feels wrong here. Oh yeah, that's the average. That's the average. That's not what I want. I want the sum. So what's the total? I would have to take that average and multiply by 5. That's the sum. So if I sum all those together, 112.80 is my answer. Oh, and I can't put units on yet. So the total is 112.80. I can't average because I have to divide by 4, not 5, right? So the total is 112.80, I think. And then S must be the square root of the variance. This is called the variance. The variance is the average of the square deviations from the mean. N minus 1 is 4. So what do you get? You get in brackets under the root 28.2, and then when you take the square root, you can now put the dollar sign and call it 531. So this is the sample standard deviation. This is the sample variance underneath, and it's a measure of deviation. It's a measure of spread. In particular, it's the average of the deviations from the mean. You take the square root because we squared them to eliminate the signs, because we weren't interested in the signs or which side it deviates from. We want to know how far away it is in total from the mean, each observation in total from the mean. So this is our sample standard deviation, which is what we got from a calculator. Like I said, I don't expect you to do these steps. I just want to help you feel more comfortable or more confident about what it is we're doing here, because I'm going to use this formula in a variety of ways, or this approach in a variety of ways. So what do we do with these numbers now? What does 5.31 mean? Are you asking about this 4 here? This 4 is from here. No, it's n minus 1. Because there's 1, 2, 3, 4, there's 5 observations. And because we are using a sample, we divide by n minus 1, not n only the population you divide by n. You'll have to watch the video again. Okay? So now, how do we interpret what does 5.31 mean? Okay, it's good, Angel. Don't forget next time. That's the point. That's why I'm going through this, that you, I know it's kind of a long process, but don't lose sight of what we're doing. So I'm trying to show you what this is all about. It's the average of the deviations from the mean, but because we put an estimate inside of an estimate, we lose a degree of freedom, so we're dividing by n minus 1, but it's still an average. It's still a sort of an average, with the assumption inherent that we believe the data is symmetric, or we're assuming it is. So now what do we do with this number? What does 5.31 mean? What does 5.31 mean? Well, what we do is we say that she spends $8.20 a day on average, give or take $5.31. So most of the time, she can spend in that one standard deviation range. Okay, so this is pocket money. This is her potential spending. So it's $8.20 plus or minus $5.31. Which creates a range of $2.89 to $13.51. So that's how we use the mean and standard deviation. It gives us a range of what to expect, most of the time. So going back to the data, how many of the observations are in that range? Well, 2 is not in that range, 8 is, 10 is, 16 is not, but 5 is. So 3 out of 5 are in that range, which represents 60%. So most of the time is like the majority, right? 60% of the observations fall in one standard deviation. So we can do this because the data is assumed symmetric, so we can say we can add and subtract from both sides. How many observations are within 2 standard deviations? So within 2 standard deviations are all of the observations. Notice this range. This range covers all the data. So you see now, by the way we use the standard deviation, we want it to be able to cover, represent a lot of the data, and in this case, all the data is within 2 standard deviations. Okay, all data is within 2 standard deviations. So there's no data outside of 3 standard deviations. Why do I care about that? Because data outside of 3 standard deviations are considered extreme values and outliers. In this case, there are none. There are no extreme values. So, observations for symmetric data, observations outside of 3 standard deviations from the mean are called outliers. And in this case, there are none. It's a very tight distribution. Any questions? So this is an example of historical data. This is an example of data where each observation is equally informative. I don't have any preference for one observation over another. I use them all as data representative of the population and calculate sample statistics. But what if my data was not like that? What if it was like this? Here are 5 observations, but that's all that I have determined can exist. And each of these have different likelihood of occurring. And this was determined by observation over a long period of time, some modeling of human behavior, and some predictions of the future and economic conditions of this student. Okay, so I'm making this up, of course. But to come up with something like this, this is actually a discrete distribution that describes the states of the world that are possible for this student. There's only 5. That's why I say it's discrete, because I can actually list them. It's not continuous. There's only 5 possibilities, and these this shows that 2 has a 20% chance, 8 has a 30% chance, 10%, 16 a 30% chance, and so on. Now with data like this, we can still calculate a mean and a standard deviation, but we have to do things differently. This is called the weighted mean, and this is called the weighted standard deviation, which is the square root of the weighted variance. It looks familiar. Rather than dividing by n, I pre-multiply by a weight, and that's like a fraction less than 1. All of the weights must sum to 1. So each one is less than 1. And as a result, or between 0 and 1, as a consequence, I don't have to divide by n or anything like that. The weights themselves will add up. So here, what's happening in this sort of an exercise is I am giving equal weight to each of these observations. I'm saying this has a weight of 1 over n. Each one has a weight of 1 over n. And so what I do is I add them up, and at the end, I divide by 1 over n minus 1, actually. How will I explain that? I'll say for the average, okay? So for getting the average, so we consider that each of them has a weight of 1 over, in this case, 5. And I pre-multiply each of them and then add them together. In this sense, in this way, the regular average, doing it like calculating an average this way, is a special case of the more general weighted mean. So what we do to get the average, or the weighted mean, is we have to multiply these. So what I'm going to do is I'm going to pull this aside. I'm going to calculate it over here. And what I want to do is have xi times pi. So I have to multiply all these across. Zero 0.4, 2.4, 0. Oh, sorry, that's just a 1. 4.8, 0.5. So the sum is actually the mean, and notice I use the Greek letter because I'm treating this as the weighted mean. So you don't have to divide anything by anything, okay? You just sum them. You multiply them and sum them. and you get 9.1. So $9.10 $9.10 is the average of this data, the weighted average. And now to calculate the variance and then the standard deviation, I have to get the deviations from the mean, square them, pre-multiply them, and then again sum them like I did here. So you need to know how to do this because we're going to do this. So you need to practice. Now a nice easy way to do this would be in Excel, but let's do it here for now and then you can practice in Excel to repeat. So I'm going to make a note here to replicate this in Excel for you. So you have to take 2 minus 9.10 and put it there. I should just do it in Excel, it'll be easier for me. So what I'm going to do is take this data over with me. And I have to flip this. So this 2, 8, 10, 16, 5. This is X. This is PI. This is deviation. Oh, I should write mean. So the PIs are 0.2, 0.3, 0.1, 0.3, and 0.1. And so I'm going to take the deviations from the mean, which is the value, minus 9.1 that we calculated as the mean. Oh, I shouldn't put 2. I want to put this column, this, like that, and then copy that all the way down. And then here, so I'm going to square each of these all the way down. And then what I have to do is pre-multiply So then I'm going to pre-multiply by the weight times the squared deviation from the mean. So this is easier in Excel. Again, sorry, it's jumping around. So those should be with PI. And then I sum them. And then I get the standard deviation. And that's it. So this is the long way. I'm just thinking if Excel has a weighted mean and weighted standard deviation calculation you can use, but this is the way you do it. This is the way you do it anyway. Yeah, for the test you can make it in Excel, yeah. I mean, you can use, I always said, you know, you can use anything at your disposal, but you just can't ask somebody. So the answer is 514. 515, I guess. We'll round it. So practice that. It turns out that so this is the conclusion. Again, like the previous, she spends $9.10, give or take, so that's how we express it in words, $5.15. So in one standard deviation, that's between about $4 and $14. Most of the time she spends between 4 and 14, so I just rounded it here. So that's how you use the mean and standard deviation. The larger the standard deviation, the more spread out the data, and most of the data should be within, not most, but like, you know, the majority of the data should be within one standard deviation. Let's see how much fits in that range. So this will fit, and this will fit. So again, it's going to be 60% of the observations will fit. And you can do 2 standard deviation. You can check if there are outliers, and I don't think there are here either. So you should practice those techniques. One is the historical data that I describe here, where every observation has equal significance or importance. So you just divide by the total once you sum them. And then here, where you pre-weigh each observation by their relative significance and then sum them. So, you know, 8 has more value than, or is more likely than the others, as well as 16. 16 and 8 are more likely, and 10 and 5 are less likely. So practice that in Excel, and that brings us here. So any questions so far? So that brings us to a discussion of density curves and special kinds of symmetric density curves that we learn about. So here is a relative frequency histogram. So a stem and leaf plot shows you all the data, and we can make a shape out of it that looks, that tells us the distribution. We can also make, when we have lots of data, we make a histogram. And if anybody needs to review histograms, have a look at how those are made. This is called a relative frequency histogram because each bar indicates the percentage of observations that fall in that class. And then what we do, just like before, is I smooth out the histogram with the idea that, well, if I had all of the data, if I had the population of data, I do think that it'll look like this. It'll have this general shape. Okay. Most of the observations will be around a center value. Some will be less, and just as many will be above. And some will be much lower, but just as many much higher. Okay, so it balances around the center. And we're going to focus on symmetric distributions in finance because we look a lot, at least in this course, we spend a lot of time looking at risky assets in the market, and it turns out that over time, if you look at historical data, they will have a symmetric distribution. Okay, so like Dow Jones index measures and like that represent a market portfolio of risky assets. The S&P 500 is another one. So those will be symmetrically distributed. So we focus on symmetric distributions, and then we have to remember, since I'm idealizing it and saying this is the population, then the center I can write the symbol mu as the mean. And on the axis here, I refer to this as the percentage of observations in the height. So if I'm interested in how many observations are to the left of the mean, what would it be? So what proportion, what p of, so x represents the variable that I've plotted, and little x represents the value on this number line. And notice I made it continuous, so this is a continuous distribution as the values go between, this is the number line from negative infinity to infinity. And we write the area under the curve. So when I see x, this represents the random variable of interest, and this represents the value that I'm looking at. So let's say I'm interested in the percentage of observations that are less than the mean. Okay, I'll just leave it with a symbol for now. So what would that be? So the area under this curve, because it's the percentage of observations, the area under this curve is 100%. We refer to it as 100% of the observations are under the curve. And I'm telling you this is a symmetric distribution. And I'm cutting it in half, saying this is the mean. The mean is also the 50th percentile. It means that 50% of the observations are to the left and 50% are to the right. So that means that the percentage of observations that are less than the mean are 50%. So P stands for proportion of observations, or percentage, probability. Why do I say it's probability? Because I'm treating this as though it represents the population. So this is all the possible outcomes. So out of all the possible outcomes, it represents your chance. So the chance of an observation being lower than the mean is 50%, and the chance of an observation being higher than the mean is 50%. Okay, try not to think about what you learned right now. Just answer my questions with, just have a look at my questions with common sense, and then I'll tie it all together with what you've learned before. If this is just a density curve, there's nothing special here. It's symmetric. And I cut it in half, and I asked you, how many of these are there? And out of the total, it's 50%. So when you see the word P, or the letter P, it means proportion, percentage, probability. It can also refer to relative frequency, or chance. So it could be all those things. So if you know that here %10 of the observations are smaller than X star, what do we call X star? What name do we have for X star? So we can express that as P, that the curve less than X star. I don't have to put a number, but I will in a moment, because people don't like X star, I'm sure. So the chance that an observation is smaller than X star is 10%. What do we call X star? close. This is called the 10th percentile. Okay, so a percentile is the value where p% of the observations are below it. So what about here? What do I call x star star? I'm not sure how you say it in Spanish, percentile. Eightieth percentile, right. So we write that big X less than X star star is equal to 0.8, and X star star is called the 80th percentile. And I can also talk about, so let me put numbers on these. Let's say that this was, I call this 58. I call this, I'll put them in a different color. So let's say this one was, actually, you know what, I'll do it later because I don't want to confuse this. Let's just leave it like that for now. Okay, so then what if I want to go, what if I ask you, what is the probability of an observation between X star and X star star? How do you figure that out? What percent of observations are between X star and X star star? Don't add. Just look at it. Just look at it and reason through it. Don't try and remember something that you didn't remember well. Just look at it and reason. So all of this is 80. This is 10. So what is this in between? So to get the area in between, you take the big space and you minus the small space. So you take 80 minus 10, so it's 70. There's 70% in here. No, 70. So this is 80, the whole thing. You take off this little piece and that leaves 70 here. So it's 70%. But thanks for being here and trying. Okay, so those are the mechanics. This is what you can do with a density curve. What's another name for X star star? It's the 80th percentile, but every position along here, because it's a continuous distribution, or just because it's a line, number line, I can think about what it's greater than, but I can also think about what it's less than. What's another name for X star star? What's another name for X star? And we'll start with star star. So if this was your grade, if this was a grade, this student was in the 80th percentile, another way to see this is the student is in the top 20th percentile. So you can speak about the other side as well because it adds up to 100. So the person's in the 80th percentile but the top 20th percentile. And for X star star, X star over here, this would be, it's 10%, it's in the 10 percentile. You could also, but nobody really says this, but it's also in the top 90th percentile. It's not really a top because it's a really bad to be in the 10th percentile for grades. But this could be another variable. What if this is in losses? This represents losses in the stock market. Being in the bottom 10th percentile is pretty good. You don't want to have a lot of losses. So you can see this as the 10th percentile. You can also see that there's 90% other people above. Okay, so every position you can look below and above. So to the left is called percentile. To the right is the top percentile. So that's just a basic symmetric density curve. The area under the density curve is 100%. And we only look at area between values, or either to the left, we can look between values, or we can look to the right. So if I write if I write, if I want to, I can also write px greater than x star. I can write it like this. The area to the right of this is 90%. That's the way I would write that. So I can talk about the area in between, where I put the lower number here and the higher number here, and use these arrows going as greater than. X is greater than x star, but less than the higher one. I can talk about area to the right. I can talk about area to the left. But area at a point, density at a point, density at a value is always seen as 0. So the probability that x equals a particular value, like 60, is 0. Okay, there's no density at a point. And that's because there's infinitely many numbers in between any points on a continuous number line. So the chance of it being just exactly 1 is infinitely, or it's unlikely. So we just say it's 0. So we already discussed here interpreting percentages and percentiles as the value such that p% of the area under the density curve lies to the left of it. And because density curves are idealized, we imagine that we have all information possible in the variable when we are smoothing out the underlying relative frequency histogram. When the density curves are symmetric, we have a special name for the center or mean of the distribution. We call it mu, we've already discussed this, and we call the standard deviation sigma. We use the Greek letters, in other words. And that brings us to the special kind of symmetric density curve known as the normal distribution. And we're going to talk about that. The normal distribution has a special spread, and it has all the properties of density curves, symmetric density curves that we discussed. It's symmetric, so the mean, the median, and the mode are the same, but it's particularly spread out. I'm going to move this. No, it didn't work. I want to cover this up. Give me a moment. So what we have that's too big. So what we do is we plot in the center our mean, and if we have a data set and we want to do this to check if a data set is normally distributed, we would just calculate the sample mean and say, well, looking at the relative frequency histogram, it looks symmetric and the mean, median, mode are about the same. So I'm going to assume normality and let the mean x bar be the population mean, and I'm going to use S, the sample mean, as the standard deviation of the population. And then what I'm going to do, just like we did for the other symmetric distribution, is I'm going to add one standard deviation and take away one standard deviation and say most of my data should be within one standard deviation. But in particular, a normal distribution was developed by statisticians that it's precisely that's better. It's precisely at an inflection point that the first, hold on. That the first observation, sorry, the first standard deviation occurs. I gotta make these straight lines. It's not the easiest. So this goes up like this. So then this begins to curve right there like that, but that's not very good. Let me do that again. This is why I like to use the thicker pen. Okay, so it curves like that, and then so for a normal distribution, it's actually 68% of the observations within one standard deviation of the mean. And if you go 2 over, so when we did this for the spending data, we found about 60%, right? So that wasn't exactly normal. Also, within 2 standard deviations, so if I go here, that's too far. So equal intervals, I'm going to go over another standard deviation. So at 2 standard deviations both ways, you have 95% of the data. So not all of it, close to all of it, but not all of it. It's 95%. And then at 3 standard deviations, there's actually data after it. The normal distribution allows for outliers. It allows .7% of the observations are between 3 standard deviations, permitting what percent of extreme values? So what percentage are extreme values? Right, not 30%. Try again. Close, though. What is it? So it's 99%. So 100 minus 99.7 is 0.3%. So that means that allows for 0.15% on this side. I have to write that again. And 0.15% on this side. So if there are 1,000 observations, 3 will be outliers. So this is not like the data that we analyzed for the student with spending money. There were no outliers, there were no observations outside of 2 standard deviations. So that wasn't a normal distribution. So these are the properties of a normal distribution in general. There's some more specific properties, but this is all we need for this class, that you know this and know how to apply it. So it turns out that stock returns, stock returns as a whole on the stock market have a normally distributed distribution. And I mentioned the Dow Jones Industrial Average and the S&P 500. So that's why we need that. Okay? So it's almost 11. I'm going to stop here, and you guys just go ahead and study for your exam. I did give you more notes. We're going to talk about correlation in Monday's class. So have a look at what I sent you before Monday's class, but obviously you're going to focus on preparing for the test tomorrow. So tomorrow morning I'll send the test early, and you guys can get started for submission by Sunday at 3. Do you have any questions for me? Okay, you mean for the test tomorrow? Yeah, you can send me your work. That's no problem, Diana. Send me an email. Okay? So we'll see you guys on Monday. I'll be in touch online via email. If you need to, you can text me. So take care. Cuídense.